All right. Today we're going to cover ionic bonds, just kind of review, and then we're also going to go over what's called lattice energy. And remember, ionic bonds, when they form, they don't form a single bond, but they actually kind of form this big lattice structure, this crystal structure. And you can see it here. One thing, hopefully, you remember from the lab is that ionic bonds or ionic compounds are dissolvable in water. What happens is the water comes around and removes the ions. And when that happens, the ions are able. Let me make this a little bigger. So the ions that are floating around in the water help conduct electricity. Remember, charged particles that have movement are able to conduct electricity. That's why the delocalized electrons in metal bonding are also able to, because the electrons are negatively charged and they can move as well. Ionic solids are brittle. So if you remember, metallic solids are malleable or ductile. You can really shape them. But ionic solids, the crystals are brittle, and the reason is because there's repulsion. So as you move, as you try to bend or move these solids, you'll end up with a plus the like charges will be next to each other, which will repel, and then they'll start to crack. Okay, so this is kind of some new stuff here. So when you're forming ionic bonds, in general, when you're forming any chemical bond, what's happening is you're releasing energy. So you have these atoms that are moving around, and what happens is they slow down when they come together, and actually bonding is more stable. And so when you bond, it's lower energy. So bonds, when you form bonds, bonds are created because they're more stable. Why are they more stable? Well, because they're at a lower energy. So to create a bond, you actually go from high energy to low energy. Well, to go from high energy to low energy, you need to release that energy. The energy, it has to go somewhere, so it gets released into the environment. And so that process of anything that releases energy, any chemical reaction that occurs that releases energy, we call exothermic. Meaning like the energy is given off, right? And actually the reason why I wrote negative here is because when you look at numbers like the amount of energy required, if it's an exothermic reaction, those are negative numbers. Now, in order to break a bond, so the bonds are stable, so you have to add energy to break bonds. Putting in energy is called endothermic, or it would be a positive number. I mean, you have to put in that energy. Endo means in, exo means out, like exo, like an exit or something like that. So we have, remember these crystal lattices. So to form, the lattice energy is energy released when oppositely charged ions in the gas phase come together to form a solid compound. So basically, lattice energy is the amount of energy released, the key is released here, the amount of energy released when bonding or creating this lattice. So, for example, if I want to make Li2O, lithium oxide, the amount of energy released is 2,806, and this would be kilojoules per mole. I mean, I won't worry about this, but you don't have to know the numbers. But the key here is it's negative. Remember, negative means release, right? Negative means exothermic. So all these numbers are negative because this is the amount of energy required to released when these lattices are formed. So, what are some factors that affect lattice energies? Like, so what makes lattice energy like bigger or smaller? So, like, if you look back, Li2O is negative 2,806. LiF is only 1,047. So we would say that lithium oxide Li2O has a larger lattice energy than LiF. Well, the question is, why is lithium oxide have a greater lattice energy than lithium fluoride? And there's two factors. One is the size of the ions. So the larger the ions, the weaker the attraction. And it kind of makes sense, right? Like, so if I have the bigger, say for example, this is the further they're away from each other, right? The distance they're away from each other would mean that there's a weaker attraction. The closer they are, the more attraction they are, because there's more interaction with the positive nucleus than the negative electrons. So larger ions means weaker attraction, so lower lattice energy. And then the charge of the ions, the larger the charge, the stronger the attraction. So if you have more charges, it'll be stronger attraction, which will equal lower lattice energy. Sorry, that's a mistake. Let me fix that real quick. So that didn't make sense, right? So if you think about it, a larger charge is stronger attraction. So a stronger attraction would be higher lattice energy, meaning it's stronger. The bond is stronger there. This can all be summed up in Coulomb's law. Now, Coulomb's law, you don't have to memorize it per se, but we just have to understand it. And so these are the charges. And then this is like the distance between atoms. But really, if you think about it, it measures the size. Like the greater the distance, the greater the size of the atoms, right? So it kind of makes sense, right? Like if your numerator goes up, the force or the lattice energy will increase. If your distance increases, which is your denominator, if that increases, anytime a denominator increases, that makes the number smaller. For example, like if you have 1/2, right, and you increase this, it becomes like, say, 1/4. Now you have a smaller number, right? So as the distance, as the distance increases, the force gets smaller, which makes sense because there's less attraction. As the charge increases, right? Here's the charge. As it increases, the number gets bigger, and that makes sense. As the greater charge means greater charge means greater force. So if the charges are the same, so here you go. Which size particles will have a higher lattice energy, right? So remember, the answer would be this one, wouldn't it? Because it's smaller. So its charges would be, so it's smaller, so there'd be a little more attraction, so this would have a higher lattice energy. Remember, it's kind of an inverse relationship. As the size gets smaller, the force increases. So this is actually lower lattice, right? Why? Because they're bigger. Okay. What about this one? So here the sizes are the same, but the charges are different. Which one would have a higher lattice energy? Remember, the greater the charge, the more the attraction, so the higher the lattice energy. Okay? All right. Okay, so what about if I ask you, like, which one has priority? Like, which one affects lattice energy more? Would it be the charge or the radius? So let's just take an example. Let's take a look at this. So here the lithium is a +1, and here the beryllium is a +2, right? Those are the charges on there. So we can say that the charge doubled. But what happened to the radius? I went from 152 to 112. So 152 to 112. Did the radius halve or decrease by double? The answer is no, right? Like if it was 152, like a decrease would be 76. So what I want you to see is that the charge actually doubles or triples more easily or more rapidly than the actual radius. And so if you don't quite understand that, just remember charges first and then radius or distance is second. I mean, it's kind of nice because it's in alphabetical order, right? So charge first, radius or distance second. So let's do some problems. So MgO has a lattice energy of negative 3,800 kilojoules per mole, and NAF has a lattice energy of negative 223 kilojoules per mole. Explain why. So at this point, let's go to the periodic table. So we're comparing MgO and NAF. So the first thing, you guys remember? It's charge and then distance, right? Okay. So I'm going to look at the charge. So Mg is a +2, -2. Na is a +1, -1, right? So which one's going to be bigger? Well, the charge is bigger for MgO. So this will have a higher lattice energy. So as we go back, you can see it has a higher lattice energy. Okay? All right, what are we comparing? We're comparing which one has a higher lattice energy, NaCl or Ki? All right, let's do it here. So let me use this color, NaCl and Ki. So let's check the charge first, right? We're always checking charge. So this is +1, -1, +1, -1. All right, so charges is the same. So now we know charge. We got to look at size. So we have Na with Cl, and then potassium with iodine. Okay, so which one is going to be bigger? Well, remember, as you go down, it gets bigger. As you go down a group, doesn't it get bigger, right? Because you add an extra energy level, right? So sodium chloride is smaller than potassium iodide. So therefore, potassium, since sodium chloride is smaller, it's going to be closer. There's going to be higher. There's greater attraction. So the sodium chloride would have higher lattice energy because it's smaller. So just to recap, I checked the charge. It had the same charge. So then I had to pick the smaller one to have the higher lattice energy. Oops, wrong one. So LIF or BAO. Let's check it out. LIF. LIF, BAO. This one's pretty easy. LIF is +1, -1. BAO is +2, -2. Immediately, bigger charge, higher attraction, higher lattice energy. Okay? CaO and BAS. So CaO is a +2, -2. BAS is a +2, -2. Oops, so we got to check it. So BAO. Here we go. BA. Where are you, BA? Here's O. Okay, and ooh, this might be interesting. What was the other one? Let me go back real quick. Sorry. BAO and hang on. CaO and BAS. I'm sorry. CaO, BAS. All right, sorry about that. So CaO and then BAS. So CaO is smaller, higher lattice energy. Okay? All right, so the last one, we're going to rank all these guys. CaO, Ki. All right, I gotta have to remember these. How am I going to do this? Let me take a picture real quick, and then we'll go that route. All right. Okay, so let me go to here. So what do we got to rank? We got to rank CaO, Ki, Al2O3, BeO, and then LIF. All right, so CaO +2 -2, Ki is +1 -1, Al2 is plus. This one's interesting. Al2 is +3 -2, BeO is +2 -2, LIF is +1 -1. So if you remember in Coulomb's law, it was like the charges are multiplied by each other over the radius squared, right? So to figure out, we just multiply the charges. So like this would have 4 this would have 1, this would have 6, this would have 2. Oh no, 2 times 2 is 4, sorry. And then this would have 1. Okay, so we already know that this is going to be the largest in terms of, this would have, that one has the highest lattice energy. Now I got to break it down. So let me look at my ones, my +1, -1s. So you got Ki and Lif. All right, so let's take a look. So Ki, Lif. So we did this, didn't we? So Lif is smaller, so it has a higher energy. So lattice energy. So Ki would be the lowest. So it has the lowest energy, lattice energy. Lif is slightly bigger. So we got those guys out of the way. Now let's take a look at BeO and CaO. So BeO is right here. And then CaO, well, then they both have O, but you can see Ca is bigger than Be, right? So that means that BeO has a higher lattice structure or lattice energy. So it'd be CaO, Be. Let me keep my BeO is a little bigger, and then followed by Al. Let me get Al2O3. All right. Hey, hopefully that helps. But that's kind of what we need to be able to accomplish with lattice energy. Okay. On the next slide, there's actually like a homework and keys and practice if you want to practice as well.